So one of you came and spoke to me about this thing which I had shown last time. So things are clustered. We were talking about galaxy bias and why galaxies are clustered, galaxy clusters are clustered, and blue galaxies, red galaxies are more clustered than blue ones, and so on. So this clustering is very severe in this particular example, but doesn't mean these kind of clusters form only in one place. Okay, if the Earth were maybe 10 times bigger, maybe there would be 10 Kenyas. So don't think of it as a single peak in the whole distribution. What it means is there could be multiple peaks. So just there could be multiple clusters forming in the universe. It's not necessary that there's only one cluster. So that's the thing. And the reason, of course, why it happens in Kenya is this. So this is a map of the altitude of the Kenya as a country. And on this side of the country, it's very high altitude. Mountains are there. You may ask why there are other higher mountains in the Himalayas and other places. But here they have a peculiar situation that they have highlands and relatively flat land. So it's high altitude and flat. So you can run, practice your running quite easily over there. So that's the reason. Okay, anyway. Okay, so now coming back to our discussion of the large scale structure. There is one major component of the baryonic large-scale structure that we have ignored so far. We've not talked about dark matter, but even the baryonic structure we have ignored. What is that? Gas, where? Intergalactic medium. That's precisely right. Okay. So what we have ignored so far is the intergalactic medium, okay? The baryons between galaxies. Its density evolution follows the large-scale structure formation and the potential wells defined by the dark matter, forming a web of filaments called the cosmic web. So the gas arranges itself into these sort of linear structures, or one-dimensional structures, I should say. They're not linear, they could be curved. And that is referred to as the cosmic web. Important distinction is that this gas unaffiliated with galaxies samples the low densities regions which are still in the linear regime. So linear regime means what? Linear with respect to time. So the growth of the overdensity is linear. So suppose in a billion years, overdensity increases by a factor of, by some factor 3, it will increase by a similar factor in the next billion years. However, once gas becomes very dense, the growth becomes nonlinear. Because if you just grow overdensity linearly, you will never form galaxies and stars. At some stage, when the density, when the overdensity exceeds a certain threshold, then gravity becomes really dominant and everything collapses. The gas collapses into to high densities and forms galaxies and stars. Gas falls into galaxies, which serves as a replenishment fuel for star formation. So don't think of the intergalactic medium gas as gas which is just sitting in the intergalactic medium. It is constantly trying to fall into the nearby galaxies. Why? Because the galaxies are sitting at deeper points in the potential well. Similarly, it's not as if once gas gets into a galaxy, it stays there forever. There are processes known as feedback, which is basically, say, active galactic nuclei or supernovae that are going on in the galaxy, that will drive the gas out of the galaxy and back into the intergalactic medium. So enriched gas is driven from galaxies through the radiatively and supernovae-powered galactic winds, which chemically enriches the IgM. So the IgM's metallicity is constantly going up as a function of time, because more and more metals are getting produced inside galaxies and through supernovae and AGN are getting thrown into the IgM. So this you have to remember. And therefore, chemical evolution of galaxies and the IgM track each other. So over time, both galaxies and the IgM are getting more and more metal rich. So now, how do you observationally detect the IgM? Or study it? First, you have to detect it. Any clues? It's very low density. The gas is at very low density. A lot of it may not even be ionized. So you can't even use the H alpha technique. Even if a lot of it may be neutral, but it is at such low densities and such low surface densities that you will never detect it with a radio telescope observing in H1. So how do you detect this gas?
If there are radio bursts in other galaxies, then the
dispersion measure is correct. So if there is a fast radio burst or something like that, that will be dispersed and you will see it. But those are very rare events. Is there some way of detecting it without waiting for something bright to go off? Can you, for example, detect it in some other way using lines? So this is the way you detect it using absorption lines, right? So let us say there's some cloud of gas here, some cloud of gas here, some cloud of gas here, right? So, and there is a distant quasar, and you're observing the spectrum of the quasar. So when that light of the quasar passes through this cloud, it will produce some absorption lines. When it passes through this cloud, it will produce some more absorption lines, some more absorption lines. And what you will see in the spectrum will be the linear superposition of all of these spectra, right? So you'll see the lines, maybe even the same lines, but they won't lie on top of each other. Why? Different redshifts. So the amount of redshifting will be different in each case. And so you will see maybe three copies of the same line coming corresponding to three clouds. You can even do this in H1, in the radio. And then if you have these neutral hydrogen clouds, they will subtract at the H1 frequency corresponding to that redshift. So you will get three H1 lines similarly. So this kind of thing has been exploited enormously over the last 25 years, absorption line spectroscopy. Yeah. Yes. So you will see many thousands of lines. We have said only three clouds here. So you could see thousands, there could be thousands of absorbers, and therefore there could be thousands of lines. Okay. Remember, if the absorber is very low density, then if the density is approaching zero, then it will not have any detectable effect. So the cloud has to have a sufficiently high column density of gas, right? From here to here, there has to be sufficient absorption. If the gas is so diffuse, so low density that it barely produces any absorption, you won't see it. Can you think of any other advantage of absorption lines over emission lines? Why are they easier to detect? They're easier to detect because the strength of the absorption doesn't depend on the distance. So if this cloud is taking away 2% of the light, okay, it doesn't matter whether that cloud is there or here. It will still take out 2% of the light. So even if it is low, even if it's very distant, you can detect it as easily as you would when it is very close. This is not true of emission lines, because the emission line, if it is very nearby, the emission line will appear strong. And when you go far away, the emission line will die down, right? It will disappear into the noise. So you will not be able to detect it. So absorption lines can be detected at very high redshifts. Emission lines cannot be detected. So here, what you are more worried about is how bright is the quasar? How many photons am I throwing into the system? So that even if I lose some photons along the way, I still detect sufficient number of photons. So you need a bright quasar, but you don't worry about and you need reasonable density in the clouds, but you don't worry about where the clouds are located. So you said thousands of absorbers will be there. There are thousands of lines here. This is known as the Lyman alpha forest. Okay. So what is the Lyman alpha forest? Which line do you think this corresponds to? Lyman alpha. That's a clue there. But see, the quasar itself is showing Lyman alpha in emission. Correct? And then as the light comes through to lower and lower redshifts, okay, there are clouds which are absorbing. So there'll be a cloud which is producing this absorption, another cloud producing this absorption, another cloud producing. So there are literally thousands of clouds here. Where will be the low redshift cloud in this forest? On which side, right side or left side? They're all Lyman alpha absorption lines. Low, left side. Correct, that's right. So the low redshift absorbers are here. The high redshift absorbers are here, right? And the highest redshift, there's some absorption lines here also. So they are very close to the quasar. And therefore you are seeing these absorption lines. Now, what are these? These are some other absorption lines. What are those? And they're not coming from the quasar. They are metal absorption lines, okay, magnesium lines and calcium lines and neon lines, all kinds of lines, which are basically at a higher redshift than Lyman alpha in the rest frame, and therefore they're appearing on that side. But they're coming from here. They're coming from the same absorbers that are producing the hydrogen absorption are also producing metal absorption. That is coming from the quasar. So this kind of thing, very bright in Lyman alpha and a very blue continuum, which means it falls as the wavelength increases. That continuum is coming from the quasar. The absorption lines are coming from the intervening absorbers. The same guys that are producing this hydrogen absorption. So suppose you had very pristine hydrogen clouds, right? There won't be any absorption lines. There are no metals, so there won't be absorption. Okay. So this is about the IGM. I move on to now other quantities that we measure for the large scale structure. The most basic quantity you can measure is, one of the most basic quantities you can measure is the luminosity function. It's basically a number, it's the relative number of galaxies at each luminosity. Okay. Now the luminosity function can be affected by many different factors. For example, the primordial density fluctuations will decide both the amplitude and the angular scale of those fluctuations will decide how many galaxies form at what time and so on. Then the processes that destroy and create galaxies are also important. Processes that change one type of galaxy into another, maybe by mergers or by stripping of gas, and processes that transform mass into light, okay, that is star formation, those also can vary. And the observed luminosity functions are fundamental observational quantities. Successful theories of galaxy formation and evolution must reproduce them. So what is this function? It's the number of galaxies at a given luminosity. And you can construct these luminosity functions at different redshifts. For example, at redshift 1, at redshift 2, at redshift 3, and so on. And this is what it looks like. Okay. Now, for the first time, I think in this course, you've seen something that's not a pure power law. Perhaps it's a power law in this section, but obviously it's curvy. Okay. And what is this? This is the best fit analytic expression to observed composite cluster galaxy luminosity distribution. Field circles show the effect of including CD galaxies in the composite. So, moment you add in the CD galaxies in clusters. So all of these, this is a galaxy cluster luminosity function. So you only include galaxies that fall into clusters, and you do it at low redshift. Okay, this is a low redshift plot. So now what kind of analytic function can we fit to this curve, to the data? So in 1974, Press and Schechter calculated the mass distribution of clumps emerging from the young universe, and they got a function of this form, except that they had mass instead of luminosity. And in 1976, one of the two authors, he said, okay, can I just try to fit this same function to the luminosity distribution of galaxies in Abel clusters? And that is the plot that you saw previously. So this is the function. Okay? The function has two parts and three parameters. Which are the two parts? This part, which is a power law, and this part, which is a exponentially decaying function. Which are the three parameters? Which are the free parameters over here? What do you think are the three free parameters? L star, N star, alpha, correct? So these three parameters are the parameters that you have to fix. This is the functional form. Now, what is this L star? It is that luminosity. It's a characteristic luminosity of galaxies, above which, so below L star, when luminosity is less than L star, the power, it almost looks like a power law, because this thing, it doesn't contribute much. But moment L exceeds L star, then the exponential decay takes over. So that is why you get that kind of, huh? N star is the number of galaxies at the L star. Huh? Sorry? That is just the differential quantity, right? Because you are writing it. So what does this quantity represent? Phi L dl means how many galaxies have a luminosity between L and L plus dl. That's the usual way of writing the differential. Okay. So L star is the luminosity that separates the low and high luminosity part. So L star is about 10 raised to 10 L B. This is in the B band. So luminosity B solar. So solar luminosity in the B band. And now you have H raised to -2. Or MB star is equal to minus 19.7 plus 5 log H. At low luminosity L less than L star, we have a power law with some slope, typically minus 0.8 to minus 1.3. So minus 0.8 you call flat, minus 1.3 you call steep. And lower luminosity galaxies are more common, as you would expect. At high luminosity L greater than L star, we have an exponential cutoff. Very luminous galaxies are very rare. And N star is a normalization. Okay, it's set at L star N star is equal to this quantity for the total galaxy population. Depending on context, N star can be a number of galaxies per unit volume, or even a probability. So these are just equivalent quantities. Note the implicit dependence on the Hubble constant via HQ. So like we saw last time, that H100 is always used, so that you don't have to worry about what is the exact value of the Hubble's constant that has been used. Right. So this is your N star. That's your normalization of the curve. This is the flat faint end slope. The luminosity function will look like this. If it has a steep Fenton slope, it will look like this, but it will always have a very rapid exponential cutoff. Okay? So L star, so faint galaxies are on this side, bright galaxies are on this side. Bright galaxies are very rare, faint galaxies can be very numerous. So phi L per dl, which is usually plotted as log phi versus log L. One can also do phi m per dm, where m is the absolute magnitude. Okay, then you have to remember not to take logs. Okay, so this is effectively d log L because absolute magnitude is like a log of the luminosity. Sometimes the cumulative luminosity function is given, which is n greater than L or n less than M. Okay, so it's the integral of the function that we plotted. How many galaxies are there which have a luminosity greater than a given luminosity, or an absolute magnitude less than some given absolute? Observational is also important to specify whether the LF is for specific Hubble types or integrated oval types, whether it's for field galaxies or cluster galaxies or whatever the environment you're talking about. And the value of H naught, since phi varies as H cube, while L varies as H raised to minus 2. So you either use this H quantity here, or you specify exactly what H you use. Huh?
We see that there's biases in the observations. Right?
Yes.
Faint galaxies cannot be seen.
Correct.
So they're there.
Correct.
So this function fits observations.
It fits observations, but after making corrections to the kind of things that you're talking about. You're absolutely right that if you just do it raw in a raw sense, then you will miss out. Even on the bright side, you might miss out. Why? Because they're so rare. Perchance you looked in some, you picked up clusters that didn't have such bright galaxies for some other really physical reason, that they were perhaps less massive clusters that were just forming. So you won't find that. So you would get a you will miscount the bright galaxies as well. But certainly for faint galaxies, you will miscount them for sure, because there's a bias. So that, I think I have a slide on them. Okay, so how to measure the luminosity function? So I'll give you one example of how to do it. There are additional complications if you are doing it in the field. Okay, but let's try to do the simplest case, which is this: we are trying to do the luminosity function in clusters, and we assume that all clusters, galaxies, are at the same distance, which for reasonably high redshift cluster is absolutely no problem at all, because the size of the cluster is negligible compared to the distance to the cluster. So what do? You bin galaxies by apparent magnitude to some limit to get this. Use the cluster redshift distance to get phi of m, and fit a Schechter function to phi of m by minimizing the total chi-square to obtain the m star and alpha. Right? Complications arise principally from trying to eliminate foreground background field galaxy contamination. So you think a particular galaxy is in the cluster, but actually it's not, and that is messing things up. Here galaxy velocities are useful. So if you have spectra, then you can confirm that yes, this galaxy is definitely in the cluster. Also, dwarfs are often too faint to measure, except blue compact dwarfs, because they have low surface brightness. And we need to apply statistical corrections to n of m using field samples. Right. So measure the luminosity function in the field. Here, obtain a flux limited sample. All galaxies brighter than a given apparent magnitude limit. Use distances to calculate luminosity of each galaxy. Form a histogram of luminosity. However, each luminosity bin comes from a different survey volume, Marmquist bias, correct? That is, surveyed volume Vmax is small for low luminosity objects and large for high luminosity objects. So you have to divide NL by Vmax over L as a function of L to create phi L, the density of objects at each luminosity. This now corrects the Marquis bias, and each luminosity samples the same effective volume. Unfortunately, this method assumes a constant space density. So if the space density is constant, then it's fine. When will this assumption be especially problematic? It will be problematic in situations where the space density is changing, right? So if a lot of mergers are happening, for example, then the space density can actually reduce of galaxies, although their luminosity can increase, but the number can reduce. So all of these complications exist. So now what is this? How do you correct for the Marquis bias? So this is known as a 1 over V max correction. So what you do is, if you know for a limiting flux, which is the limiting flux of your survey, you calculate what is the maximum distance to which you can observe the galaxy given its luminosity. So Flim is fixed, but the luminosity of every galaxy is different, and therefore the distance to which it could be observed in your survey is different. And using this Dmax, then you define a Vmax. It's the maximum volume within which you could detect it. It's just 4 pi by 3d square kind of sphere. And so see this L raised to Vmax is L raised to 3 by 2, and 1 over Vmax therefore goes as L raised to minus 3 by 2. That's the curve that's shown here. And then you actually make that correction. So for every galaxy, you will have a different value of Vmax because it will have a different value of Dmax, which will depend upon its luminosity. So you use this formula while calculating the luminosity correction. So because here, of course, these are field galaxies, you cannot make the assumption they're at the same distance. You will know the distance because that's the only way you can get L for the galaxy. So for every galaxy, you have an L, you have a Vmax, you make that V over Vmax correction, and then you plot the luminosity function. Okay. So here what's happening is luminosity is increasing, then it's decreasing. I mean, the numbers are increasing with luminosity and then decrease. Right. And these high luminosity objects don't require a correction, but these objects require a correction because the volume surveyed in such cases that their Dmax is very small, whereas over here the Dmax is very large, and you may not end up applying any correction. Okay. But this is an old approach. Now there is a sort of more maximum likelihood based method, which was devised first devised by this paper, Blanton et al. 2003, and this is the most common method that is used for correcting the luminosity functions. And you have to use that. There is no such thing as trying to publish an uncorrected luminosity function. It has no physical value at all. Okay. So early work showed that the Schechter function is a good fit to many galaxy samples, but these two quantities can depend on sample depth, cluster or field, cluster type, morphological type. Which one is more important? So people said in general, cluster luminosity functions are well fit by a Schechter function, have similar L star. Alpha is often steeper than in the field. Okay. So the alpha of clusters is steeper than in the field. There can be a dip drop near this kind of absolute magnitude. There can be an excess at higher luminosities for CD galaxies. So what are CD galaxies? These are, I've already told you, these are galaxies that sit at the centers of clusters at the deepest point in the potential well of clusters. There are these galaxies, and any small galaxy that happens to come too close to the cluster center simply gets swallowed up by these galaxies. So they're typically ellipticals, and typically they're very, very massive. So now people said, okay, why are we seeing different luminosity functions in different situations, right? Why is the value of alpha and the value of L star not sort of universal? Okay, so people asked that question, and the answer was that it seems to arise from different proportions of these different morphologies, and there is a systematic dependence of morphology on the environmental density. So there, it turns out there are more ellipticals, S0s, and dwarf ellipticals in clusters, while more spirals and dwarf irregulars are in the field. This is evidence for a morphological dependence on galaxy density, and this is known as the morphology density relation, which was discovered by Dressler in 1980. So what Dressler found was that he said, okay, I'll take some 50 odd clusters, and in every cluster, I will count the density, local density of galaxies in different parts of the cluster, and I will measure what is the morphological fraction. So he's typically near the centers of clusters, you have the highest density of galaxies, and it falls as you go radially outwards. So he went and counted painstakingly. It took him a few years to do that. But what he found out, near the centers of clusters where the density is high, the morphology is dominated by ellipticals and lenticulars. As you go outwards, further away from the center of the cluster, the density falls, and now the morphology is dominated by spiral galaxies. So spiral galaxies are there on the outskirts of clusters, but in the innermost parts of the clusters, you have essentially all ellipticals and lenticulars, right? And this dip occurs at the changeover from normal to dwarf galaxies. CD galaxies clearly had a different history, probably growing by accretion in dense galactic environments. So this is now, this is the luminosity function. Okay. Why does it seem to be going up this way? Because the faint galaxies now are on this side. You're plotting it in increasing absolute magnitude. So what they did was, okay, let us just decompose it into luminosity functions of ellipticals, of spirals, of S0s, and dwarf ellipticals, and add all of them together. Then you get the overall luminosity function. So the overall luminosity function varies from field galaxies to groups to clusters, like low density clusters to high density clusters, only because the relative fraction of the different morphologies changes in a systematic way when you go from low density regions to the highest density regions. So that's all that's different. So here you have only spirals and dwarf irregulars, and that's why this luminosity function looks different than that. But if you decompose it in this way, then it seems to be universal. So spiral galaxies have a luminosity function. S0 galaxies have a luminosity function. Elliptical galaxies have a luminosity function. That luminosity function can change as a function of time and therefore of redshift, but it doesn't change as a function of anything else. So this is a cluster, Able 1689, and this is the CD galaxy that sits at the center of the cluster. And the CD galaxy is more luminous than the luminosity function predicts. Then this, it doesn't fit on the function. And interestingly, in 1976, Schechter had already found that. So these are CD galaxies, these two data points. Okay. Field circles show the effect of including CD galaxies in the composite. So this is not just one galaxy, this might be multiple galaxy points that are binned, but these are both CD galaxies. I mean, both those bins correspond to CD galaxies, and they deviate. Okay. So this may be telling us something interesting about how CD galaxies form and evolve. They don't form and evolve exactly like the other galaxies because their merger history is totally different. They are like cannibals sitting at the centers of the cluster, just eating up everything that falls. So now we look at what may be the physical origin of the luminosity function. So making galaxies involves at least 2 steps. What are the steps? First of all, dark matter halos must form, relatively straightforward and well understood. Baryons must fall in and make stars. This is complex. This is complex physics. We don't understand that. So now I'll just have to give you a flavor for how these things work. So what you do is there are what are called dark matter simulations. So you start with, you know how much matter was created in the Big Bang. You have some estimate for how much dark matter would have been created. Dark matter doesn't seem to be, it doesn't interact with light. So there's no way to convert dark matter into light and destroy it. There doesn't seem to be any way of converting light into dark matter. So dark matter is dark matter. It always stays as dark matter. So given some distribution of dark matter and given small perturbations in the density is not absolutely uniform. There are small perturbations that we know exist because we can see perturbations on very, very small scales, more small amplitudes in the cosmic microwave background. So these perturbations will grow over time. And why will they grow? Because gravity is only an attractive force. So over time, things will tend to come together. So the overdensity in certain regions of the universe will grow. Now, these concentrations of dark matter are called as dark matter halos. So initially, small halos will form. And then small halos will merge with other small halos and form a bigger halo. And then this big halo will merge with a neighboring big halo, which has formed in a similar way. And it will eventually form larger and larger dark matter halos. And it is inside these dark matter halos that galaxies form. Why do they form inside the dark matter halos? Because the gas feels the gravity of these dark matter halos and slowly begins to accumulate inside them. And that's where you get higher densities and stars. So the cosmological simulations follow dark matter from initial slight perturbations to make many halos by hierarchical assembly. Okay, so this is called hierarchical assembly of dark matter halos, because small halos merge to form bigger halos merge to form even bigger halos, and so on. The mass distribution of these halos follows the Schechter form. So if you take your simulation and try to measure how many big halos I have, how many big small halos I have at any point in time, and you can still fit that Schechter function, power law plus exponential, to that, and you will get the mass distribution of these halos. Hence, one might expect a Schechter function for the galaxy mass distribution also. Under what assumption? This you can see, you run a computer simulation and you know that the dark matter halos follow the Schechter form, right? Why should galaxies also, we went and observed the galaxies, we fit luminosity functions, everything. They also follow the same equation. Why are the two are correlated? Under what assumption?
Gas should also be similar to the initial distribution of gas. Be similar to the initial distribution of dark matter. So when they found halos, gas should also come with that.
So that is a reasonable assumption, given that gas just follows the gravity, right? I mean, gas cannot go off in its own direction. It has to go where gravity goes. And the dark matter is also going where the gravity goes. So getting gas concentrated in the same way as dark matter halos is not a problem. What we are measuring when we are measuring the luminosity function, are we measuring the concentration of clustering of gas, or are we measuring the clustering of something else? We are measuring the clustering of stars, because the luminosity is not coming from gas, it's coming from stars. Right? So what here you have to assume is that the mass to light ratio is relatively constant over large ranges of luminosity. So the efficiency with which galaxy form stars should be proportional to the mass of the halo within which it sits. The observed galaxy mass function has completely different upper cutoff and lower slope compared to this, the theoretical mass function that you have. Specifically, there are too many huge and dwarf halos in simulations without huge and dwarf galaxies in the real universe. Yeah. So this works. The mass function and the luminosity function match each other except at the two extreme ends. There are too many huge halos and too many dwarf halos without any corresponding galaxies. Okay. So look at this. So this is the galaxy luminosity function with V over V max correction, everything applied. These are the dark matter halos. This is the Schechter function for the dark matter halo. What is here shown by the dashed line is the dark matter halo divided by 6. Because you can say that, okay, dark matter is 6 times more common than luminous matter, right? So therefore, it should have been over here. I mean, if this curve had exactly overlapped with the dashed curve, everything would be okay. But it is clear that it matches up reasonably well in this middle range, but on both sides, it is problematic. It is deviating. Right. So there is the dark matter guys are predicting you should have many more halos here, but you're finding less. Over here also, they're predicting you should have found many more galaxies, but you're finding less. Here you should have found many more dwarf galaxies. So any ideas why this may be occurring? Any thoughts on that? This is harder to understand, but this one is simpler to understand. You can't form large number of dwarf galaxies. What's the difficulty? Will dwarf galaxies form in shallow potential wells or in deep potential wells? Shallow potential wells. So when you have shallow potential wells and you have supernovae going off in the dwarf galaxy, what will it do? Huh?
So stars and gas.
It'll push off gas outside the galaxy. Okay. Usually it's hard to push stars. Huh? Stars are very dense, massive objects. But gas can be thrown out of the galaxy. Once the gas gets thrown out of the galaxy, what will happen to star formation? It will quench. It will stop. Okay. Then again, the gas has to slowly fall into the galaxy, which takes a long time. And then it may grow a little bit, but again, it will form supernovae. Again, it will throw out the gas. So it's easy to understand why these galaxies are missing. So the halos are there. The gravity is there. But you have to also model the force that acts against gravity, which is feedback from supernovae and AGN. So that is the thing. So the supernovae and the AGN are the things that are preventing large number of dwarf galaxies from forming. And that is why we don't see them. And the other end, you tell me what might be happening at the other end. There are a variety of factors that could be responsible here. One is that there isn't yet enough time. So similarly, feedback processes can also happen that can slow down because you have to form a galaxy here before you can form a galaxy here. right? Galaxies have to merge and so on. It may be that we haven't given enough time. The universe is not old enough to form galaxies of this scale. In the future, galaxies may form which have masses that are closer to this line. But this is just one factor because the discrepancy is very, very large. Discrepancy is very, very large. There could also be, yeah, go ahead.
Anytime during the dark matter halo simulation, that it fits the high mass, like if we evolve it further and further,
Yes.
the dark matter, the other way.
Meaning dark matter halos and galaxies are close to each other. See, there is always a time lag. That factor is there.
In dark matter halo simulation, we evolved it for a long time, therefore it looks like the right side picks up.
No. Time-wise, it's the same time. So the dark matter halo is you stop at 13.7 billion years. You don't go further, and further that shape may change.
Because
So-
there is no feedback in dark matter halos.
There's no feedback in dark matter halos. Yes, there is no feedback at all. Because dark matter keeps on clustering, it only feels gravity. There is, once you form a high mass dark matter halo, you cannot reduce its mass even by a gram. Dark matter stays. Dark matter does not interact with the baryonic matter in any way. You have supernova, AGN, you do any kind of explosion inside the galaxy. It doesn't affect the dark matter at all. At all.
What about the gas going out?
It will pull the dark matter along with it, but because the luminous matter is much less in mass compared to the dark matter, because of that it affects it less. There will be some effect. The dark matter may get pulled out a little bit because of this feedback, but the mass that is thrown out is not very large. Because baryons itself are low and you don't throw away all the baryons. Suppose a supernova goes off in our galaxy, how much of the baryons is it going to throw out? Not even 1%, not even 0.1%. Even if an AGN turns on, powerful AGN, it's not going to throw out more than a very tiny fraction of the baryonic mass. Unless it's a dwarf galaxy in which it can throw out much of the baryonic mass. Okay. So how do you actually form galaxies? So a very popular technique, which was there for many years, is that so in gray is shown the dark matter simulation. You just run on a computer, okay? And it's very, very simple actually, because you don't have to worry about GR effects and so on, because they only operate in very strong gravity field, okay? So simple Newtonian dynamics operates here. So you essentially solve Poisson's equation, del square phi is equal to minus 4 pi 0 at every epoch and at every location to recalculate at every time epoch, you recalculate the potential, and you know the velocities and masses of every particle that you have in your dark matter simulation. You can use those forces to correct their, figure out how their velocities will change. And you then go to the next epoch and you recalculate the same.
Why is GR not required? It's a
Huh?
huge-
Huh?
Why is GR not required? It's a huge area of length scale, right?
Length scales are huge, but
Causality is-
causality is there, that is built in. So you, for example, you have some matter here, it will not affect, so the speed of light kind of propagation of gravity, that is there. But you don't solve GR equations, what I meant by not including GR. So it's not Einstein's equations that get solved, it is Newton's law which gets solved. Right. So then the gray gives you your dark matter distribution at any point in time. And in these so-called semi-analytic galaxy evolution simulations, then you say that, okay, if there is a halo of this density, and if it is surrounded by other halos of that density, then I will put an elliptical galaxy inside that halo. So in every halo, you basically paint on galaxies, like it's shown here literally today. And these are with young and old stellar populations. And so what this tells you is that, of course, early on in the universe, 2 billion years after Big Bang, there were only blue galaxies, star-forming galaxies. Later on, as the universe aged, the fraction of star-forming galaxies were restricted now to the lower density parts of the universe. And all the densest parts are populated with old galaxies, elliptical galaxies. So this is how, so once you do this, then you can try to match up the numbered. So you can even create things. We did this 20 years ago, which is once you know the dark matter distribution, once you know the semi-analytic models, what kind of galaxies they're producing, can we just create a mock image, an artificial image, and then compare that image with what you see with the real telescope? And this we did with a software called Galix 20 years ago, and created mock images. So now if you do all of those things, the semi-analytic prescriptions, so this is the galaxy simulation with the gas physics involved, with all the feedback processes now put in also. And now these semi-analytic models seem to fit the real observations quite well. So which means if you make images based on this thing, you should see the image look, simulated image should look indistinguishable from the real image. And we got very close to that. Now we got into trouble in recent times because the luminosity functions of galaxies, the observed luminosity functions, which is your purple curve over there, that has changed with the advent of JWST at high redshifts. Because JWST seems to be finding a large number of very massive galaxies at high redshift. So the data themselves have changed. So obviously the simulations have to be modified in order to, so the main debate with JWST is, does one need to modify the cosmological parameters? Whole cosmology is wrong, maybe Big Bang cosmology is wrong, or can we just tweak the simulations so that they reproduce the observed results? And so far it seems to be, by tweaking the simulations, we will be able to still reproduce the observed results, where currently there exists a discrepancy. So that work is.
It is only the high mass.
The low mass is very difficult to observe. So, I mean, if you have a dwarf galaxy at high redshift, this discrepancy is only at high redshift, by the way. There isn't much of a discrepancy at low redshift.
Like, it's pulled up even at shorter times. Our idea that, universe is not old enough to get high mass galaxies might be. Like
Okay.
Said,
yeah, change the cosmology. Yeah, so that is they can just about do it now. In the sense that they can form by tweaking the efficiency of star formation, tweaking the initial mass function of stars and so on. They can just about reproduce the changed luminosity function. But it's a close call. If there could be, maybe in 3 years, what I'm saying now may be retracted. That people say, no, something's wrong with cosmology. There simply isn't enough time to create such massive galaxies in such a short time. Then we may have to say, no, either there might be minor tweaks. You change the value of H0, you change the value of omega matter, omega lambda. Or worse is start questioning Big Bang cosmology. Okay. So the virial theorem. Okay. The virial theorem can be applied to any system of stars that is in a steady state such as elliptical galaxies, evolved star clusters, evolved clusters of galaxies, etc. It cannot be used for any system that's in a time varying state. Cannot be used for merging galaxies, newly formed star clusters, clusters of galaxies that are still forming, still have infalling galaxies, etc. Can it be applied to the solar system today? Are we in time equilibrium? Yes, definitely. So you can measure the dynamical mass via the virial theorem. Okay? By dynamical mass, one means the mass tracing both the dark, which includes both the dark matter as well as the luminous matter, any matter that feels gravity. Consider a spherical elliptical galaxy of radius r that has uniform density and which consists of n stars, each of mass m, having typical velocities v. Can we measure the typical velocity of stars in an elliptical galaxy? Yes, the answer to that is also yes, because you can measure the velocity dispersion of these galaxies. And that is quantified by this quantity sigma. Okay. And then this is just the statement of the virial theorem, where this represents your kinetic energy. This term represents your potential energy. And this 3 by 5 is for a sphere. Okay. Where P for a uniform sphere of mass m and radius r. And this tells you, like you just rework the algebra terms here, the mass is proportional to the dispersion velocity square times the radius divided by capital G. So can we measure the mass of supermassive black holes using this? Absolutely. You can measure. So instead of measuring velocity dispersion, people measured velocities directly of stars that are going around the supermassive black hole at the center of the Milky Way. And they use exactly this formula, put V square instead of sigma square. They know what is the R is the distance between the black hole and that particular star. And you can measure the mass of the black hole. And that is how we have measured the mass of the black hole at the center. So even black holes in small galaxies can be measured, because you can see what is the change in, what is the velocity dispersion at the center of galaxies. That's a measurable quantity. Okay, so what is meant by velocity dispersion? At every point in the galaxy, you measure the Doppler shift, right? And the standard deviation of all those Doppler shift measurements is the velocity dispersion. And that peaks at the center. So you take the peak velocity dispersion and you plug it, that sigma value, kilometers per second, whatever it is, into this, and you get an answer for the mass. And by using this technique, you can measure the barrier, the dynamical mass, which is shown on the x-axis, and the baryonic mass, which is, of course, measured independently using some other technique. And this line is where the dynamical mass is 6 times the stellar mass. Okay. Why? Why 6? Because omega matter is approximately, dark matter or all matter is, omega dark matter is approximately 6 times the baryonic matter. And all galaxies seem to lie more or less within this zone. So the assumption that up to 6 times the dynamical, and this is where dynamical mass is equal to m star. Okay. You may ask, how can you have points in this area? How can the dynamical mass be lower than the stellar mass? Well, stellar mass is higher than the dynamical mass. And that is because, I mean, there are errors in measurements in computation of both the stellar mass and the dynamical mass. So these points are not physical. But most galaxies, and there are some 38,000 galaxies that have been plotted here, and they're all within that range. So how would you use the virial theorem to estimate the mass of a virialized cluster? Same idea. So how will you know if the cluster is virialized or not? This is something that you probably won't be able to answer. So I'll tell you the answer to that. If a cluster is merging, right? Uh, it uh, it shows a very, it doesn't show a smooth morphology in the, especially in the X-ray, which is tracing the gas. So some gas will be shocking, some gas will be clustered, so all kinds of non-uniformities are seen in the gas. So whereas if you see a uniform distribution of uh, uh, a circularly, radially symmetric distribution of the X-ray emitting gas, then it's virialized. Okay? Which means it's the virial theorem can be applied. Now, how will you use the virial theorem to find the mass of the cluster? You have to use this, again, same formula. And what will you use for sigma and what will you use for R? How will you measure? R, let's say, is the radius of the cluster. You can measure distances and say, okay, this cluster is 2 megaparsec in radius, 1 megaparsec in radius. How will you, what will you put here? Velocities of what? Yes. So the galaxies are moving around. Every galaxy is moving around the cluster, right? Each with a different speed. What you will measure is the radial projection, the velocity projection. You'll have to convert that somehow into a 3D dimensional speed. And you don't use the speeds directly because the speeds may average out to 0. But the velocity dispersion, which is the standard deviation of the speeds or the velocities, that will not be 0. Actually, the velocities, not the speeds. And then you can plug that in as a sigma. No, it's the visible radius of the dark matter halo. You're right, not of the visible cluster. So in 1937, Zwicky did exactly this, what we are proposing to do now. He measured velocities in the coma cluster, and he said virial theorem should hold here. I will plug in the values of v square. I know what's the radius of coma. And he found the mass to light ratio is 300. And we know the mass to light ratio of clusters should not be that high. Anything, even galaxies mass to light ratio everywhere is around 20 at most. So he said, I'm finding a lot more mass. The galaxies are moving too fast in the cluster. The velocity dispersion is too high. Something is wrong. And of course, nobody took him seriously for 30 years. So he discovered dark matter. He already discovered dark matter in 1930s. Okay. So this is, what do you think? Is this is a cluster, and superimposed in blue and white is X-ray emission. Do you think this cluster is virialized? Huh? No, absolutely not. This is a merging cluster. Two different clusters are merging. So the hot gas is all disturbed and dispersed. Okay. Yeah. So we can stop here. And in the last lecture, I'm going to cover a little bit more about these kind of things and then go on to cosmology. And in cosmology, I'm just going to introduce you to the big picture and what are the relations in cosmology that are independent of the cosmological parameters, that only depend on redshift. Sorry? Dates of final exam. Yes, good you reminded. So shall we fix 27th? Do you have a time for the other exam? Which other exam you're having on 27th? Quantum mechanics. Who's your teacher for that? Huh? Debarti. Okay. So I am okay with anything. How long is that quantum mechanics exam? 1 hour. Okay, so we'll do it, whatever is in the morning. So shall we then fix it? Then we can, she'll have to take the other slot. It's in the afternoon, after 2:30. Excellent. So let's do it in the morning then. Shall we do 10 to 12 on September 27th? Yeah, I will send out an email. I will book this room. And your exam will be similarly patterned on the first exam. Okay. Did you feel the first exam was too long? You didn't have enough time? Because we can extend it. I mean, we can make it 2 hours, 15 minutes. Or... Yeah. So let's say we'll make it 2 hours, 15 minutes to start with. And if everybody is really stuck, you want more time, we'll go to 2.5 hours. So 2 hour, 15-minute exam starting at 10 a.m. on 27th September. Okay, the weightage here will be double. So the exam will be approximately double the length. It will cover now all 14 lectures. And obviously, you will not get too many questions from the first. You'll get more questions from the second half of the course. But you may get one or few questions from the early part of the course. Good. So now we meet again tomorrow, right? At the regular time. That will be the last lecture of the course.